Yeah, maybe we'll get started. Yeah, so we talk about representation learning again. So this is a kind of a last lecture for this part, part one. Yeah, basically the representation learning we talk about last two times, autoencoder as well as the variation autoencoder, if you recall. Autoencoder using reconstruction, passing through a bottleneck that serves representation. Representation is for encoder. So in the autoencoder, there is also decoder for generation. So in the sense of if you think about the view of autoencoder, it always serves the purpose for generation, right? So you have first doing encoder, doing recommendation, then doing decoder, doing generation. The question is that needed to learn representation using generation, right? You could do that as we show in the autoencoder and the variation autoencoder. But this lecture goes back to representation learning, except to rethink this problem to say, maybe you do not need a generator in order to train say encoder or representation learning. Now the question is how do you do that, right? If you think about the autoencoder view, you do best reconstruction, best generation through a bottleneck, reduce dimension that serves the purpose. Here we need to introduce some other principles. The principle essentially is kind of an invariance principle, contrastive learning. This is something we want to talk about. So there's a different view. Turns out this also is a very successful view, used quite a bit. And variations of this. I mean, contrast learning is only one of those methods. There are some modifications, but have a similar flavor, basically, in terms of learning representations. So once you get this, then you probably capitulate to some other ideas if you see that in the literature. But anyway, so this is, we will talk about this representation learning using a different point of view. And there are two papers which comes out. The first one is the original one. This one make these particular type of methods popular. To make it work, actually. The second one is a follow-up. It has some newer ideas, but mostly focusing on from image to sentence. So we mostly talk about the first one. The second one, we just quickly go through that. You just say, oh, there are some extensions. So that's all. Yeah, okay. But it actually can be an effective way for text embedding. Even nowadays, variations of that has been used to create embeddings. Okay, so let's talk about the main part of this, talking about the first paper, to explain what it does and so on. As you can see, this one is a later work than autoencoder and variation autoencoder, right? Autoencoder, we know it's probably in the 80s or whatever. Variation autoencoder is I think it's maybe 5 years earlier, or around than this paper, and then this one. So let's think about just to review the autoencoder. I've already summarized that, but then we will go through that again. So for the representation, this is what we focus on here, right? Essentially, to think about the encoder in the autoencoder setting. Essentially, the Z should capture semantic information that can be useful for downstream tasks. The downstream can be classification, as we will use that, or can be generation, whatever other things. It can be used to quite a bit of things. basically the compressed information of your data, like X. So why do we need to learn an actual decoder, right? So just to recall, I mean, this is basically the point of view we talked about the last two lectures. The view would be kind of just learning that reconstruction, right? Decoders needed because reconstruction based, because I mean, you have to come out with reconstruction, come out with this decoder. So this lecture try to move from this reconstruction to something like invariance and similarity in the sense of how do you define similarity, we will soon see. To the basically, yeah, in the latent space. So essentially, similarity is in the latent space, invariance in the original space. You try to, so this actually is slightly different. We will say a bit more about, the difference about these two point of views and how do you learn this representation out of that. The key part is this one is a purely learning of representation without any decoder, right? This is a clear distinction from VAE or denoising autoencoder. Now let's just recall that. So the main thing here we want to do is just recall our memory about what we are doing with denoising autoencoder. Then we'll bring up this invariance. So denoising autoencoder, we can also do VAE, but let's just focus on this one. You first do a perturbation and noise, right? And then you encode to a latent kind of a semantic space so that it just represent all your functions into a vector or something similar to a vector. And then you decode, right? You have this training objective is reconstruction. So the idea is you can tolerate noise. Here, actually, noise is a different structure than typically than your image. That's why you can denoise, and then you do that. So encoder produce latent code, which is a representation. And it will have enough. You can differentiate noise from the inputs, and then you can actually reconstruct X. So basically, this is essentially what we do. Just to refresh your memory about the key idea in the last two lectures. Of course, VAE has some probabilistic model, but nevertheless, it's the same idea. So there's limitations. The main limitation is the following. So we will see the examples later on, then we'll comment back to say what you cannot do with this view, right? So what kind of things you are not. For example, one thing is two inputs have a slightly different pixel level mapped apart, right? You cannot necessarily be, I have a shift image. If let's say I have a cat image, right? Cat is on the left-hand side of the image. I will shift to the right-hand side of the image, right? But then it's still the same image with one cat. Then you are saying these have the same semantic meaning. But from reconstruction point of view, it's very difficult to make them the same reconstruction, right? So they are different. And this is called the invariance, right? This kind of shifting environments. We talk about the CN has this property. Usually they try to exploit this property. But essentially, this kind of invariance to say, oh, my semantic shouldn't change. There are a set of transformations you can do, say, oh, my semantic shouldn't change with this kind of change, this kind of transformation. So reconstruction essentially force some kind of low-level details, which may now need like texture and so on. So. And we really want the same semantics, right? Like the shift example with the similar embedding. Turns out the reconstruction cannot do that because, if I do the same embedding, then I don't know the position about the cat, either it's left-hand side or right-hand side, right? Then I cannot reconstruct because I don't know which one should be, whether I should reconstruct to left or whether I should reconstruct to right. Therefore, if you're just looking at this particular view reconstruction, you will not be able to map them to the same. You have to differentiate because they have a very different pixel representation. So that's a key. This is where I say, let's say I started with this idea, cat on the left-hand side of the image, cat on the right-hand side of the image should be the same semantics. How do I do that? Right. So this is where the contrast learning comes in. Basically, they try to implement this idea so that they actually goes back to the same. Okay. So I hope that's clear. If maybe I should draw a picture here. Basically, one is left, one is right. Right. Basically, two cats. I mean, basically, you cannot make it the same so that you can reconstruct exactly back, because they're different position. They have a completely different pixel level information. So yeah. But anyway, so this is what you actually can do with contrastive learning. So this is the basic idea. Now let's talk a little bit about, we will change a little bit the notation because we don't have a decoder anymore, right? So in the VAE, we have encoder, decoder. In the contrastive learning, encoder is just F. So basically we use F. F is encoder, right? There's no decoder. So there's no decoder, right? So basically we just use this this is basically what we want to use. No decoder, we only learn an encoder, which we just call function f, right? Well, later we will add another function, which is auxiliary function. It's just, we'll talk a little bit about that. But essentially, all you learn is f. You do not have a decoder. It's an encoder. So we just use f. Yeah, okay. So this is our current formulation for this contrastive learning with this notation. Now let's look at what we want to do, right? From here is something essentially tells us what exactly we want to do when we go from reconstruction to invariance. So instead construction pixels, just like VAE, right, or autoencoder, we generated two transformed views from the same semantics, right? Transformation, for example, if I have a cat, right, I just shift this cat, right? This is one rotate this cat, another. We can see some other transformations as well. Basically, X goes to something. Now we say, these two transformations, they are preserving your semantics. Therefore, they should be mapped to the same representation. Fx1 should be very similar to x to the 2, right? So, yeah. So this is we want to enforce. And the objective function is created such that this is enforced. Basically, you want this one to be closed. Actually, there are some modifiers later on we will see. We will talk about that. This is to do with this projection head we will introduce. But roughly, the most intuitive level, that's it, right? So key ideas, preserve all information to reconstruction, right? So this one preserves semantic via invariance. Invariance is special by 2. Now there's one issue, which if you think about that, right? How do I make it to be 0? Why do not wait for everything to be 0, right? So if I make everything to be 0, then of course they are the same. Then there's no differentiating power. So the only resolve is say, I don't want to make this to be 0, everything to map to be 0. There are different ways to do that. In the contrastive learning, the way to do that is try to put different images not from the same X apart. So we will see that. But there are other ways to implement this idea. But essentially, if you say the same image, different transformations, map to the same. Also, if you guarantees that throughout the image, they are not mapped all to the 0, they have to be somewhat spread, then you are mostly down. You can have an objective function which can learn this kind of functions. And we will talk about the precise function which used in this contrastive learning. So because this is a kind of one of the first work, try to explore this idea. here is basically the idea, right? So if you look at that, what it does is the following. So you are first you start with image, right? This image just have this original image from your data set. It's unlabeled, by the way. So when I say x0, x1, just make it 0 and 1. Actually, it could be 2 zeros. It's the same. Basically, it doesn't differentiate really digital 0 and 1 because the data to train is unlabeled. So you do not tell it's a 0, 1, you just tell there are different images in your database. So this data, you perturb that. So this is a 1. This particular, if you look at that, it's a little bit of rotation. It's actually the same image, limited rotation and shift. So it's like here, it's a shift to the left, right? This one is rotated a bit to tilt it a bit, right? So this one is again the same. It's a shift rotation. So these two are two different transformations, which assumes you are preserving your semantics, like the digits, what the meaning of the digits, right? But then you are basically have different views. And now you say, okay, I'm mapped to my encoder. So this is a transformed image, mapped to my encoder, right? Here, this should be close. This is a different image. Here, we just write it as 1, but it could be still another 0 even. So it's just a different image. You have two transformations, right? These two guys should map the similar. Then in the contrastive learning, you can implement other ideas. You say, okay, I don't want everything to map back to 0, everything to collapse to 0. Therefore, I need something to say that the overall the data should be far apart, right? They have to, so similar data with the same transformation, close, data starting from different image transformation will be pulled apart, right? So that's basically the idea, okay? Once you implement it, then we'll come back to the loss function. But once you implement this loss function with a little bit slightly different trick, so we'll talk about that. Then you are actually be able to do representation learning. So I hope I mean, we will later on we will go through the math, right? So math is not that hard. It's not like VAE. We have a much more complicated math, but this one is not that hard. But nevertheless, this is the intuition. Okay, so if you understand this one, then you map to the math, and then you're okay. Any questions so far? Right. So yeah, this one just what I already mentioned. First, this unsupervised learning, right? We are pushing different views, even they represent the same digit. Here, I just write that to be 0, 1, but it could be 2 zeros. Okay, they are also pulling apart as long as they are beyond to the different images. Okay. So yeah.
Digit, do you still expect them to be a bit closer in the latent space?
Eventually, learned representation will be this way, but this particular is just doing that at the image level because it's unlabeled. You cannot tell whether they represent the same digits or not. But after learning, because somehow even they are putting apart, but because they have some shared similarity. So because one, for example, 1 of 0 can be translated to pretty much like the other 0, right? With a certain transformation. So therefore, they will learn to be clustered together. Yeah. Okay. Yeah. Yeah. So yeah, I think this is a good question. But essentially, this is a way is say you can do that unlabeled. Even you don't know the labels together, somehow you just use these heuristics, you still will be able to learn meaningful representation. Okay, so this is a framework, general framework, right? So if you think about it, this is a different philosophy. This is a philosophy of learning representation. We try to maximize the agreement about augmented views of, sometimes this is called data augmentation. They are also used for classification. You generate the data, you say, oh, this data is the same semantics, so as original image. Then we can use that for classification and so on. But essentially, augmented view of the same image using a contrastive loss in the latent space, which we'll describe later. Okay, this is a high-level view. Sample and images, right? For each image X, generate 2 random augmentations or transformations, basically. Essentially, this should be semantic preserving transformations. You cannot just arbitrarily transform a cat to dog is not good, right? Transform something. Yeah. Mostly, I mean, these are just low-level things. We will see some more detailed example later on in that paper. Basically, different transformations like cropping, right? So that shouldn't just change the size, like shifts, like rotation, small rotation, not a big rotation. Like distortion, blurring, and so on, or color change, and so on. So these kind of things, you see that, they shouldn't change the meaning of the image. So use a contrast loss to learn embedding so that the embedding is closer to that than the other. So basically, this is just the description, just the text description map to the previous slides. Previous is just the more of visual illustration. This is essentially the same thing. And again, here is the actual system diagram. This introduced a little bit of G now. We can start working with F directly, but for the particular approach used by these basically by these people, right? So by these authors, they are using a different G. We will talk about this G later on. But essentially, if you want, you could work with this Z. Z is the embedding space in our notation. G is just mapping the different. So this is always a representation. G is introduced so that it's learning slightly better. There's an explanation of that in the original paper, which we will mention later. But F, here is the encoder, right? So this one is one image. This is another image using the same transformations, semantic preserving transformations. They should map the same, right? So basically, transformation, this is augmentation. F is encoder. For example, you can say ResNet, or you can say transformer, or whatever. Z is a representation, and then G is actually projection height. It's usually it's MLP. We'll comment on that. This one is one of the non-trivial things about this paper. So somehow they discovered it's better to do this way, and they have explanations. We'll come back to that. So essentially, representation and the loss is computed at U, not at Z. You could compute at Z, by the way. It's just the reason to introduce this is mostly just purely performance. After you're doing this one, you compute the loss at here, you have better performance, right? You have a better performance. So that and there's an explanation, but otherwise you could do this. But essentially, this is G, and the U is for the contractive loss. Contractive loss, we will soon talk about that. After training, so basically you discard G, you only keep F, right? F is your encoder. G is just for loss calculation. It's a part of the loss calculation. Now let's talk about the contractive loss, right? This one, as I mentioned, if you look at this, this is the actual system program. Also, we'll have the code. You can see the code. Essentially, it's coming from the U. So loss is at the U level, right? So you have a UI, UJ, you compute the loss, okay? So here is the loss. Contrast loss is normalized entropy scaled. You have an entropy like 0.2 or whatever. So this one, and the similarity of UI, UJ as vectors. And then you basically, this one is like the softmax, right? And the log likelihood. So this kind of a cross entropy. If you look at the similarity, these are similarity of UI, UJ. So in the embedding space, how similar they are. And the similarity is a pretty standard way of doing is you can either do inner products or you are doing the cosine. And here we use cosine. Cosine means basically the angle between these two vectors in your embedding space. You normalize. Normalized usually it's a convenient, it's better because you know you do not have the scale effect. Sometimes scale is problematic. Like a lot of normalization, right? So this one using two normalize so that they all A divided by A norm will be in the unit sphere. B divided by B norm is unit sphere, so the inner product will be the angle between these two vectors. Cosine angle, yeah. So basically, this is a computer loss. Now you have x ui uj is the image from the same image. You also have from the other one, right? You also actually have others. So you are looking at n data from the original. Essentially, this n data, you will be sampling 2n images. For each data, you look at you use the image from the same, right, in above. Image from below, you actually will not, it's pulling apart. If it's actually, if you look at it's pulling apart. Basically, this loss function it's a cross entropy, right? So basically, you think about that. This loss function try to make x ui uj's this the angle or cosine angle. Cosine is larger, means angle is smaller. Basically, they are close to each other. Imagine this one close to each other. This one because in the denominator, so they will be pulling far away from each other. You do not want to compare eye to eye. You only because you know the scale can be very difficult. So basically, you cancel eye to eye. You only do eye to k not equal I. Basically, k is to say all the other images. So you start with an image, your test, right? You generate two n augmented, right? 2n augmented, right? So each image generate 2, right? For the ones which are coming from the same image, you put that here to encourage that to be close. Otherwise, you put that below to be normalized away. But you remove I to itself for each eye. You just look at that. So yeah. So this is a this is basically contractive loss function. When you have a batch of n image, you're starting with generating 2n examples. Yeah. Okay. So so basically, you know, this contractive image. So total objective, right? So basically, over batch is basically, I mean, this one is basically reinterpretation of a previous view, just make it more concrete. 2n views, sample from this guy, 2 augmented per image. For each image k, right? You form a positive pair. Basic image. You have started. You generate 2, right? Generate 2. K, right? Basically, they generate 2 views. These 2 views are positive pair. Then you define loss based on previous one. Previous is the one which given these are 2 are positive. You could because you start with k to compare with anything else, any other images. So you have denominator, and then your the interpreter basically you try to classify your matching image. So you think about each image I, right? You are generating a matching image J from the same image, and the rest 2m minus 2, because you want to ignore these 2, will be the negative image. Then you think about the classification problem. You say, okay, I want to pick the one which is closer to my the matching image by using this cosine angle as my classification scoring. So that one should be the angle should be as large. The similarity should be as large as possible, and all the other similarities should be as small as possible, close to 0. And then you are basically saying, yeah, you are basically doing that. So basically this is what it actually try to imply. So this loss function essentially try to guess the other image by using the embedding space. You can think about this. So yeah, this is basically a loss function. So once we have this particular loss function, then we just implement it, then we can train the model. So that's probably pretty much it is. So the other thing about the data is this is discussed in this paper to say, oh, they want to put a projection head in this particular algorithm. Now let's say the pipeline, right? So this is a representation. You are learning this guy, and you compute the loss on U, not on Z. So why is that, right? So the key, of course, is it gets you a better performance. But then there's a reason. Why is that? So this is a projection space for contrast loss, not at the latent space. The encoder produced representation that we want to reuse for downstream tasks. It's always the case. You can either use for generation or use for whatever other things, right? So now the projection head maps to a new space where the contractive loss is applied. So this separates, right? So the representation and the contract loss space. The reason is following. Empirically removing G, right, significantly decrease downstream evaluation performance. I want to say significant. Some, if you look at the original paper, there are some decreasements. It actually works, even you work with this. It's not saying you are not this completely disaster. It's not a complete disaster. It's just not as good as this guy. So when you say significant, there are some degrees of this evaluation performance, right? So basically, this is observation. So that's why it's introduced. But why do we want that, right? So one explanation, of course, it's increase your performance. Otherwise, there's no point to increase putting that. So, but what is the explanation? The explanation is the following. So it's given by this one talked about in the paper. So I'm just copying what they are saying. Contrast loss enforce invariance to the augmentations, which is desirable. That's the philosophy about this particular loss function. Actually, one thing to observe is some information used for the downstream task may not be invariant. So this causes a problem. Basically, when you say, I only want invariant ones, then you are actually reduce you're giving you're too much. You're essentially right. You are giving too much. So basically, G allows that discard the augmentation specific information in U and preserve the richer information. Basically, says U will be the environment specific. It's only thing environment, but the environment may not be enough. So Z will actually has more richer information. If I want to criticize what they are doing, the only thing is they are not really say, oh, let's say if there are richer information, how should I enforce that to be Z? It just say if you do that particular structure, it works. Then that's all it says. Rather than say, let's try to move back. So, for example, I could put, I'm just saying as example, I would say you could put the reconstruction loss in Z, right, as a weaker loss. Just combine different loss, and then you have a decoder, but then I'm just giving an example. Then you say, okay, that preserves the richer information, right? So in Z. But nevertheless, it's not. So basically, it just say, I just discard this information. But just for granted, this one has a richer information than you, and this richer information also will be useful for the downstream tasks. So in other words, G absorbs the constraints induced by the contractive loss. and therefore you give richer information in Z, and hopefully Z is better because of richer information. Although there's no enforcement of that, right? Just to keep in mind, this paper doesn't introduce any essays enforced to say the richer information I get to Z is indeed better. If G is identical, then it's the same as you're applying loss direct on Z, right? In that case, you still learn, it's just not as good. So that's all. Then basically, you say both good representation and the contrast loss, and some loss may be contradictory. It doesn't have to be contrastive or invariance. So this essentially, this just repeating what they are trying to argue why this one is good. So you need that, right? But practically it gets a better result. Okay, so let's so taking that view, taking the experiments that they are doing, basically you just have to have two heads. One is the encoder, your true encoder, your true, and then you just plug in NGZ without additional constraints. Then just compute the loss, and it will discard this G. Okay, so that's what it is. Data augmentation. So this one is, I want to say a little bit, this also differentiated with the denoising autoencoder. If you say, oh, our adding noise is a transformation, right, in denoising autoencoder, then this one is a little bit different, even philosophically. You want a really large change, right? Augmentation basically defines the invariance. It's not noise. It's an invariance in the sense that they preserve the semantic meaning. Adding noise, usually noise has a different structure than your data. When you have an invariance, it's actually moving within the data. You can think about the different way, right? Your data space, there's noise space. Noise are different from data. So adding that, you want denoise, you really want to tell data from noise. Here you just say data has some invariance property, and if this looks like data, I transform that also looks like data. Therefore, what I want to do is I want to learn this invariant. They're all within the data, right? So, and they usually use a little bit stronger augmentations. Stronger means from a reconstruction point of view, you actually hard to reconstruct back if you after this augmentation, right? It's not for reconstruction. With small changes like noise or like whatever you could add, but for the data augmentation, that's also one. Even though this look like adding noise, it's quite different in terms. You can say strong augmentation versus weak augmentation. Common augmentation, random crop, resize, flip, right, color distortion, and so on. Yeah, weak augmentation will be more identical, or you're adding something which is orthogonal to your data, just like noise, right? So and then it's not the right thing to do here. Right. So basically, yeah. Yeah, I think I will quickly go ahead. Yeah. Yeah, here are the examples given in the paper. So this is our original image, right? Cropping, you just look at a part of this animal. Basically, then it's hard to reconstruct the original, right? Think about the reconstruction. It's not suitable for reconstruction, but you could tell it's probably a dog. I don't know. I mean, so but still, you just hopefully they are similar. But this one is something, right? So you're getting part of that, and this color, right? And you have a different color. Of course, it doesn't change much. Rotate and you remove part of that, right? So you try. Remove color actually interesting. Later on, we'll see something back when you have a master language model. This is a kind of a little bit related to this denoising, but here, yeah, here is this and so on. So these are this kind of a transformation considered there. But you can roughly, some of that is similar to the denoising autoencoder, right? But most of that are not quite. Basically, they have a larger augmentations. Okay, so here's the algorithm. So putting everything together, once you define the set of the augmentation, then what you can do is the following. Input, right, an image. We just look at one batch at a time. You have a temperature, you have a networks, you have augmentation operator, right? So for each image, this is your original image batch, right? And then you're starting to do that. Sample 2, right? You put that to be k and k plus n. This is according to the implementation we have later. Computer representations, right? So this is done. Computer projections, and this is where you have a loss. So there's nothing else in between this to say, I want to put additional constraints on Z. Then compute these similarities, right? This is for all pairs. So if you have a 2n, right, you look at the pairs, you don't have to have the similarity, but essentially it's 2n squared. So this is a number of pairs you have. You have contrast loss. So this is basically defined for each of each I. Then basically define this J, right? So basically, yeah. Yeah. Basically, actually, this contrast loss should be this is your final loss over your batch. Basically, this contrast loss should be applied k and k plus n, and then reverse because it's not symmetric here. It's depend on I, right? So your I compared to all the other image, and then you also have the other view VOJ. This is VOI, this is VOJ, and then you have VOJ, VOI. So basically, this is that's about it. So basically, this is the whole algorithm. When we look at the code, it's the same thing. We can go over that again, but this is basically algorithm. The key idea again. So maybe just reiterate. The key idea is you have a same image, right? You generate similar images from this same image. Just examples in the previous slides, and then you enforce that to have the similar representation. In the representation space, they are close to each other in the cosine angle, while it's not cosine not close to each other for the other images or other transformations from the other images. Okay, so that's eventually you update F and G simultaneously in your training. In the end, you just discard this G. Yeah, question? Yeah.
Metric loss in number 4 if one of the images is augmented and one of them is original. Shouldn't it just be like the loss for the original image instead of the other way around too?
You could do this with original, but here they are doing with 2 augmented. There's no original involved. They all both pair also both are augmented. Both are augmented. I think that's just a little bit richer. So assuming it covers more. If you're just working with original, it's a little bit not as rich, right? Because they can augment it a little bit, yeah. But both are augmented, yeah. No original image. The original normally starting with generation. If you look at this slide, it's a sampling to augmented. Only this one appear, but then in the loss function, it's never shows up. Yeah, it shows up both. It's all the augmented image shows up. Yeah. Evaluation. So basically, this one is just for that paper. So that is also pretty standard evaluation in a lot of other settings. essentially, oh, how do I tell my embedding is good, right? We can do generation, for example, right? Here, of course, this one for generation is a little bit because it's a semantic, so it's not as precise in the generation space as, say, autoencoders, right? So classification. So you are trying to train encoder, and how do you evaluate that? So given a labeled data set, right, freeze F. So you train, for example, on the ImageNet, you have an image encoder, unlabeled, let's say. Then you say, okay, now I put the labels back for the ImageNet, and then I will freeze my F. F is trained unsupervised. It doesn't see the label. So it's kind of a fair game in some sense. You get a lot of unlabeled data, right? So, and then you train a classifier with this labeled data, but with a F frozen, right? So you just train a top layer, and then you measure the accuracy. So this is a pretty standard way for a lot of this kind of representation learning. If you look at the literature, this is the kind of things you do. Alternatively, you can also do the nearest neighbor, another thing, because when we say, oh, similar images should be close together, right? So you can look at the nearest neighbor. That's another way. Yeah, but a linear probe is something which is pretty typical. Strong this accuracy means you learn good semantic. Basically, this is how you justify. You always justify representation learning to check whether they are useful for certain downstream tasks or not. And the simple test is this kind of classification problem. Nowadays, people test on more complex problems as well. So VA versus this, we will just try to say what's the difference. I mean, again, so basically we just reiterate because these are quite different approaches. AVA, last two lectures, we have reconstruction learning. So contrasted learning is they generate two different views, right? If you think about that, and these two, and we can remove this one just conceptually. In algorithmically, we need the U1, U2, but conceptually we can stop here. But essentially, that's all. And this tutor is a perturbation of the image, and this one is a reconstruction of the image. So they are different. Reconstruction, contrastive loss. Preserve full information, preserve the invariant, and one argument when you say invariance is not good enough is here, right? So it's your representation probably have more than invariant, but when you compute the loss in U, it's fully invariant semantics. Yeah, so that yeah, decoder required. This one no decoder, although there is something called the G here. This one is for convenience. This one is not always needed, but it improves performance. It just say invariance is not sufficient for downstream tasks. This guy has more information than here. Here is where you are invariance. So no encoder. Okay, so let's just take a quick look as for the projection head. This is simple. I mean, this encoder is what we see before, and you know, I think this one probably is a little bit different than the other, but it doesn't matter. I mean, this is just CNN. Each time you have a convolution, you have a max pooling, convolution, max pooling, and so on, right? Later on, I just say you have to do a global pooling here. It's slightly different. We can also, instead of using global pooling, we don't, but here it just slight change, but nevertheless, this one is basically this pulls over. This is a 3 by 3. This is 64, right? 64 channels, 3 by 3 size, and you pull that to be 1 by 1, which means after this global pooling, it becomes 64 by 1 by 1. So it's basically 64. Then you map to the encoding. So this is projection as is just simple MLP. They tried both linear and nonlinear. They claim the little bit of nonlinear helps. So, but essentially, you can have a simple projection. So it's basically one hidden layer, right? So 2-layer neural net, and then you get this. So basically, it's pretty standard design. And then once you do that, you can say I will train this guy. Okay, so let's look at our loss computation. And this one just implementation, PyTorch implementation of what we actually talked about earlier. Essentially, it's just the algorithm, the code we rewrite in PyTorch. Here is a forward, right? So it's encoder, this is F, right? This is G. So you start with F, which get a Z as your this is a batch, by the way. Maybe I should add this size. That and this G. This one is forward. Yeah. So then you get Z and U. But here maybe I should look at the contractive loss. Contractive loss, you have U1, U2. So basically, typically what you do is you simulate 2 U's from the same, right? So basically Z, you generate you generate in the inference time you don't need the U, right? So this one is for the training, this forward. But generally, what you do is you are computing 2 transformations, and then for the contrastive loss, you have a U1 is one view, U2 is the other view, right? So you do a concatenation here. Basically, it's a original batch size of n now becomes 2n, right? You concatenate these 2 views. And then this guy is a 2n by 2n, this symmetry matrix. Yeah, so this one first normalize that. Basically normalize that, just to say each one is 2 norm is 1. And then you do dot product. This one is doing this dot product, essentially 2n by 2n, right? And then you mask. This one is very similar when we look at the attention. I think it's next class is next Monday's class. It's kind of related, and there's also mask. It's very similar to this attention mask. Essentially, you mask out your current. Basically, mask is a very large negative number, right? So what happens is when you add these guys to a large negative number, then when you cross entropy, right? Compute cross entropy, a negative large number in a cross entropy maps to the softmax max to 0. So basically, you just ignore. Ignore means very large negative number. Okay. So this guy and attention mask is later on we'll talk about is also the same thing. They're also using very similar to this cross entropy. Yeah. So that's all. Yeah. So that's about the loss computation. It's just some PyTorch semantics, and then you calculate. So it's not too long. The code is always not an issue. Again, for all these kind of questions, you just need to make sure the semantics match, and then that's all. The training loop, yeah, basically you what you do is you are you train, right? So you generate the 2. This one already. Actually, in the loader, it's already generated the perturbation. So perturbation, I didn't show the loader because if you know the PyTorch, right? They have the transformation. The loader already gets you the 2 transformations. So this guy, this is a Y. Since this is unsupervised, we don't need a label. We just need this perturbed of the same image, and then you basically get U is what you want. You can disregard G in your model, right? So you get a U, and then you compute this loss function with this U, and then what is yeah, whatever then basically you do the backprop. So that's about the whole thing. Here is what you actually see when you have this contrastive learning. So this is just a picture about they are separating. So I just have 3 digits. These are MNIST. Digits 0, 1, 2, right? And this is a mapping. Oh, actually, how many? I believe this is 32. I need to check. Yeah, I believe this is 32 dimension. But then they use this visualization. You can see they are somewhat separated, which means they are learning reasonable representations. And you can also check the code. It also have a classification accuracy. Turns out, actually, if you just train on this with a contrastive learning, it does lose some information concerning if you just test classification, but they're doing a much smaller dimension. So in the 32, and I think MNIST also is not large enough. When you do the contrastive learning, usually they require much larger, like ImageNet or even larger images to train. But still, you know, when you train that, you can see you find something reasonable, and this one can be used for classification purpose, and you can use these features. This one I believe is 32. Maybe I'll double check and add the mark here. And then, but the code is provided. You can play around with the code yourself. Yeah. So yeah, so I think that's about it. This is about. I think then we are done. So mostly we are talking about this paper, contrastive learning. I think the key idea again is if you look at the autoencoder versus contrastive learning, the key idea is the invariance, right? So no decoder, no generation, but pure representation learning using invariance. So. Now let's talk about a little bit this very quickly after this paper. So this essentially is a follow-up paper. Applied this contrastive learning, the same idea to sentence embedding. Sentence embedding is very useful. Even now, a lot of people doing this kind of I mean, for the LLM, we probably don't talk too much about that, but there are some cases in the retrieval augmented generation, right? They need to embed things into a vector database and then retrieve those. We will see the retrieval example, but here you can use this kind of embedding, these kind of ideas to train this sentence embedding. And even some other techniques are pretty good embedders. They are using at least part of that, even mixed with some other techniques. Part of that is using this kind of contrastive learning. So this paper is kind of very useful, and they do have an embedding trained, which is provided. But basically, not necessarily state of the art now, but still, you know, it can be used. Contrast. This is okay. The title is basic contrast applying to the sentence embedding. Simple contrast learning of sentence embeddings, right? So if you think about image, the representation and the embedding, they are similar. So when we say embedding of an image, representation of an image, they can refer to the same thing. So here is also say it's a kind of an embedding of a text or text passages, not only sentences, but it could be paragraph, could be an article, and so on. We keep the same goal. So the same goal is x still goes to z equals fx, right? And we make a positive, we still form pairs, right? So if you recall, we will have pairs. The positive pairs should be close, negative should be far. So that's the basic idea. The main difference in this paper, they also talk about the little supervised and so on, which we quickly go over. But the key difference is how do you generate the two views. So for the image, if you think about the way we manipulate the image, right? So we try to change the image to a rotation, to a translation, and so on. And hopefully that doesn't change the semantics. One question is, can we do that for text? When we do the manipulation of text, making a different text, right? If we can't, what we can do, right? Nowadays, actually, it's easier to do that because you just ask the LLM to rewrite the sentence, right? But when it was, this paper was there, it was not that way, right? 2021, there was no LLM then yet. I think actually the GPT-3 probably came out at that time around. But maybe a little bit later. But the GPT-2 probably is not powerful enough, and also GPT-2 probably they are not accessible to them. So basically, at that time, you can think this pre-LLM era. So you cannot ask LLM to rewrite your sentence, right? How do you create different views? We know it's possible to do that for the image. Here the idea is, okay, we don't want to manipulate text, right? So, but then what do we do, right? So this is their solution. So that's actually works. So it's kind of very interesting. So essentially, dropout, we talked about that before, right? Dropout, you could create a different, let's say I have an F. If I do dropouts, the forward will affect the forward in the training mode. So different F will produce different views. Of course, what's interesting is that this one is sufficient just to train this contractive. But then basically that's what they are saying. So unsupervised augmentation by dropout. So this is the key idea without modifying the original data. Given one sentence, feed twice to the same transformer encoder with independent dropout masks, right? You can generate two dropout masks, and then you just feed to the same. And then you have two representations. They should be the same, similar, right? Dropout hopefully doesn't change your although there are some perturbation. And then the claim is this one be sufficient is kind of interesting. You have to test on that, right? You cannot just have this idea without test. But essentially, these are the positive, and you again you create a 2N data. So similar, very similar strategy than before. You create many data, you have N sentences. You create 2N pairs, 2N representations, and then you others in the negative, this one positive. You apply the contractive loss, which we already defined before, and so on. Then you can get this problem. This avoids discrete text edits, right, which can change the meaning at that time. So I would just say now you can get these text edits for free using LLMs, but not that, right? So dropout is only augmentation in the unsupervised setting. They demonstrated that actually they trained at that time is a pretty good sentence embedding. So you could you could still use that. I can give an example. Yeah, but then that's so only augmentation, and that also works basically. So this is something you can get out from that. So basically, the idea is instead of doing this explicit augmentation like images, a dropout could replace that, and sufficient. Okay, so loss is the same, everything else the same. So they basically say, oh, I mean, these semantics, text, small modification could be difficult, right? So replacement, if you want to do some kind of this kind of editing, and it may not be right. So yeah, cropping, and it's not good, and so on. So yes, it's just hard to come out with the right thing. So yeah, so basically this is keeping the sentence context fixed. Yeah, this is before LLMs. So, LLM, I think as part of the issue can be addressed, right? But, you still have, you could use, you still have maybe generate not diverse enough and so on. But nevertheless, yeah. So basically, yeah, basically that's what it is. So, projection heads. Yeah, there's another difference. We can say, oh, do we need projection heads? The claim is you could use, again, you still could use, but they said it's not as important as in the original SimCLR paper, right? SimCLR, we have they claim this is very important. And here it's not necessarily important. Encoder is a large pre-trained transformer, and so it's also strong. So basically, it's probably don't need that once you have that. So, but anyway, so yeah, so that's that's another difference. But you could add, but if you want, you could also add. There are always variations you can play with for this kind of. Basically, you need consistent with the basic ideas, right? Then you can think about what to add on or what not to add. They also talk a little bit about the supervised. Oh, there's. I think there's questions. That's a good question. So yeah, I mean. I think depends on the things. Usually we don't do. I believe it should work something. Maybe we should do that as homework, try out. But because you have a stronger, more explicit ones, they are not probably as effective, right? So you can always make something. Which one is more effective? You can also combine different ideas, right? So basically, yeah. So, but dropout is a general technique. All I can say is, yeah, you could, if you have no alternatives, you want to generate things differently, then certainly this is something to try. Yeah. Yeah. So basically, yeah, let's look at the supervised setting. I mean, supervised say you have more positives from the same sentence. Again, this is a little bit LLM. So at that time, there are a lot of studies on this kind of so-called natural language inference. Now it's already, nobody's interested in this problem anymore because LLM already solved those. But essentially, they create a lot of data. The data is say, oh, I will say some sentence A, right? And after that sentence B is inferred by the A. Then they regard as a positive pair because there are data like this. So they try to use positive as hypothesis, so-called entailment also, but essentially, negative is with contradictory, and so on. Other negatives remain in the medium batch, and so on. So basically, two dogs are running. You can say there are animals outside. This is implied by the well, I think it's running outside, but these pets are sitting on a couch. Then certainly it's not. It's negative, right? It's not entailed by this guy. Anchor A is surfing on the sea. Yeah, and there is a man. So that's certainly inferred. And whereas a business suit is not, because it has nothing to do with. It could, I mean, surfing on the sea with a business note, but first it's unlikely, but also it's not inferred by that, right? So yeah, basically something like that. So then you can create that, and then you can do some contrastive learning thing. Essentially, contrastive learning, you can think that as in the embedding space, you want to do a nearest neighbor kind of a classification to say what are the positive, what are negative pairs, right? These give you the positive and negative pairs, and then you use this thing. And Okay, then what you do is the following. So you are supervised sim CSE. You basically you basically do this. Yeah, you basically make it small and so on, right? So basically you push away in the batch and so on. So basically, so that's that's pretty much what it is. So after training, you can just directly using that. Yeah, I think we just quickly go over. It's not also it's not as important as now for these for these. But basically, yeah. So basically, but again, constructed learning is still relevant now. It just particular this kind of constructions may not. So I think we will probably skip those. You just aware of that. You could use other signals inside in addition to the dropout if you have really, which can be positive, aligned, right? Sentences. For example, you can also use LLM to generate positive aligned sentences, right? So that's another thing. And for the purpose of training embedding itself is still useful nowadays. The sentence embedding, that is separate question than LLM. Right? You can, but you can say I want to train embedder. What I do, I mean, if you want to use this kind of contrasted learning, you can create all kinds of things. One example is this kind of LM created, or the dropouts, or whatever other things, different ideas. So SimC SE embedding and retrieval example. So here I'm just showing. I mean, how usually people use the embedding. They can use because a lot of things we'll talk about in the second part. So a lot of things are solved by LLMs. So they are, I mean, even classification and so on. They could be used for classification, but people less so. But still, retrieval still is application which has to rely on this kind of embedding. So how do embedding? You could use other embedders. Doesn't have to be this contractive learned embedding, but as I mentioned, quite a bit of some even current ones they use ideas of a contractive embedding inside. So this is still relevant for retrieval augmented generation or other applications about retrieving documents from query, right? So embed each sentence into, let's say you just have different sentences embedded into your application. And then a question is, a person is reading a book, right? So this is this query, and you'll find the best one. And this one is actually used, again, that's also provided in the code, using actually using this CSE embedding. I'm not using another, you can apply other, but they're embedding. And then you just compute embedded this kind of sentences, right? Embedded this query, computing the similarity score. So as you can see, I mean, the ones in the sentences, sentence is just some made up sentence you can check in the example. So someone is reading quietly in something, and this is closely related, and yeah, and something again, I mean, it's kind of reasonable. I mean, this one, even there's no book involved, it's closer to reading a book. And these are closer and gradually becomes less closer, right? So basically, it's a small corpus, which is made up corpus. You can take a look, and then yeah, basically, so this is it's kind of effective. Yeah. Finally, I think that's all. So this is about give you different ideas about how do you train representation learning. Next time we will have exams, right? So the exams mostly are covered by the lecture slides. So you read that, and you can also take it to this to the exam. And you probably want to read that anyway. So because otherwise you get an idea. Essentially, it's a very conceptual. You look at the sample questions, so not very difficult. Basically, as long as you understand all the lecture, you should be fine. Okay. So any questions? Yeah, oh, yeah.
Main contribution from like contrastive learning is the contrastive loss that's used in training.
Contrast loss is, yeah, it's kind of how to create those positive and negative pairs, I would say. Because contrast loss is like a differentiate positive and negative. This is this essentially is a cross entropy, right? Yeah.
So like, is this idea kind of also like, is it easily plugged into like more modern architectures, like it's like diffusion models or like even with like transformers?
Oh, those are for different. Those are, I mean, a lot of that for generation. So this one is a pure representation learning. And this one is, of course, very related to attention, which we'll talk about next after part one exam. Yeah, it's very close related to that. Yeah. Okay, so if no more question, okay, that's it, and good luck for the next class, the exam. Okay.